Welcome back everyone. I'm Professor Farida Baksamusa and this is your class Physical Geology 001A, and today we are going underground to explore the fascinating and vital world of groundwater. Let's begin by recalling that fresh water makes up only a tiny fraction of all water on Earth, and most of that is locked away as ice or as groundwater. Although we rarely see it, groundwater supplies drinking water for billions of people, irrigates rocks and sustains rivers and wetlands through dry spells. Yet, because it's hidden, understanding how it works and how our actions affect it is vital for a sustainable future. Imagine pouring water into a pile of sand. Much of it quickly disappears. That's groundwater at work. Water stored in tiny spaces within rocks and sediments beneath our feet. These underground reservoirs are not vast lakes or rivers, but networks of minute pores and sometimes fractures that together can hold enormous amounts of water. In most places, we access groundwater only from shallow depths, usually the first 100 meters. Deeper sources exist, but the water is often lower quality and much more expensive to pump. But not all underground materials hold or transmit water the same way. This brings us to two key concepts, starting with porosity. Porosity is the percentage of open spaces in a rock or sediment and is crucial for determining how much water a material can store. Some rocks like sandstone or unconsolidated sand and gravel can have high porosity with large spaces between grades. Others like granite or compressed clays have much less. Remember, there are two kinds of porosity. Primary porosity, natural openings formed during sediment accumulation or rock formation, and secondary porosity, new spaces created later such as fractures, cracks or cavities dissolved in rocks like limestone. It's important to note that high porosity doesn't always mean you have an excellent water source. That depends on another factor, how well the pores connect. That is permeability. Permeability describes how easily water can flow through these pore spaces. Let me give you a nice example by drawing, say this is your sandstone or a rock and it's got pores, right? This is porosity, simple terms. Now permeability is how well they are connected. Because they flow, of course it's holding water, but will they flow? That is determined by how well these pores are connected. For a groundwater system to deliver water efficiently to wells or springs, it needs both good porosity, space to hold water, and high permeability, connections that let it move. Sand and gravel typically allow water to move freely, a reason they're great aquifers. Clays, while they can hold lots of water, trap it so tightly hardly any can flow. This distinction is crucial. Even the most waterlogged clay will be a poor source of a well, while a fractured sandstone or limestone can supply abundant groundwater. If an underground layer is both porous and permeable enough to supply usable water, geologists call it an aquifer. If it's too tight, acting as a barrier instead, we call it an aquitar or confining layer. Let's link that to real-world examples. Sand and gravel, well sorted and unconsolidated, make excellent aquifers. A layer of clay, in contrast, acts as an aquitard, restricting flow and protecting underlying aquifers. Even hard rocks like granite or basalt can be usable aquifers if sufficiently fractured. Unconfined aquifers are open to the land surface above and can be directly recharged by rain or streams. Confined aquifers are trapped between aquitards, sometimes under pressure, leading to the phenomenon of artesian wells, where water rises on its own if tapped. Now that we know where groundwater is stored, let's ask, how does it move? Water enters aquifers mostly in recharge zones, usually higher elevation areas exposed at the surface. From there, it moves slowly, driven by gravity and pressure differences, through the interconnected pore spaces toward lower elevations or points of discharge, springs, rivers, or wells. The boundary between the unsaturated, mixed air and water, and saturated, all water, subsurface areas is the water table. Groundwater flow is remarkably slow. Typical rates are centimeters per day, sometimes just centimeters per year, especially in tight rocks. This slow travel time has profound implications for both recharge and contamination. How do we access this vital but hidden water? Wells are our primary tool. By drilling down to the water table, we can pump water to the surface for use. But every time we pump groundwater, we lower the pressure near the well, causing surrounding water to flow in. The effect is a localized dip in the water table called a cone of depression. If pumping from several nearby wells draws the water table down too far, neighboring wells can go dry. Sustained over pumping can result in wells that once flowed freely eventually drying up and can even impact surface water in connected rivers or wetlands. In extreme cases, like in parts of California, groundwater levels have declined meters over decades, causing issues such as land subsidence and saltwater intrusion. Now, because groundwater is so important and so vulnerable, governments use observation wells to track long-term and seasonal changes in water tables, water quality and aquifer health. For example, British Columbia operates a network of observation wells. Data from these wells show the effects of drought, recharge from winter rains, and the impact of human pumping. Patterns show how water levels rise during wet winters, fall during dry summers, and how longer-term trends can indicate if we are using our water sustainably or risking depletion. Increasingly, water laws require licensing and careful study to ensure both human needs and the needs of the ecosystem are met, balancing extraction with maintaining stream flows and wetlands. While aquifers are naturally somewhat protected from pollution by layers above, contamination is still a major risk. Once polluted, groundwater is exceptionally difficult and expensive to clean up. Contaminants come from leaking landfills, underground fuel tanks, agricultural chemicals, or poorly managed septic systems. Even natural sources such as arsenic in minerals can pose risks when aquifers are pumped and chemistry changes. Two main ways to prevent contamination. Prevent rain from carrying pollutants down by covering or containing potential surfaces. Use engineered barriers like landfill liners to keep contaminants from reaching aquifers. If a plume of pollution does enter groundwater, it may slowly move towards wells or streams. Remediation often requires pump and treat strategies, removing and cleaning the water, sometimes manipulating groundwater flow to contain the pollution. Now let's wrap it all up. Groundwater is a dynamic, interconnected system formed by the interplay of geology, climate, and human action. Each subtopic, porosity, permeability, aquifers, flow, extraction, monitoring, and contamination control, builds on the last. Our use or overuse of groundwater links surface and subsurface systems and impacts both human society and natural ecosystems. Understanding how these pieces fit together is fundamental, not just for science, but for making wise decisions that keep clean water flowing for generations. Thank you so much for joining this lecture. Make sure you read your text, you answer your questions, you lab well, do the discussion forum well, and if you have questions, I'm always there to help you. Thank you, and I'll see you for the next one.